Hey, Physics 20s. As you can see here, we have skipped ahead, not a felt pen, skipped ahead a whole bunch to, to lesson 6 in Unit 5. Again, any of that other stuff that you look at, that's fine. It's a bit extension for these COVID times, but lesson 6 is one that we really want to focus in on. So if you're not already there, please open up your workbooks. So that's again Unit 5 up to lesson 6. Cool. So this lesson is all about getting into gravity and well, I mean, not quite where we're at now, but getting into some of the really big ideas of gravity and some of our common ideas about gravity. So it all starts off with people looking up at the stars and wondering what the heck's going on. I'm sure that you've done that at some point in your life. If you haven't, go find some dark space and go look up at the sky on a clear night. It's amazing what you can see. Even just a cheap pair of binoculars, you can see some pretty cool stuff. So throughout history, people have been using stars for navigation. People have been wondering about the stars and the planets and how they move and what's going on up there, and even to this date. So here's a person thinking about it, and here's a pretty cool time-lapse photo of the stars going around. So here in the center of this, we probably have the North Star or Polaris. And that one lines up perfectly with our North Geographic Pole. I shouldn't say perfectly, but pretty close to our North Geographic Pole. So that one, if you were to focus your camera on it and just leave the shutter open, it looks like that one's not going to move. And then it looks like all of the other stars go in perfect circles like this around it. And from this point of view, and this is the point of view that people had for the longest time, from this point of view, it kind of seems like everything is rotating around the Earth. And that's honestly what people thought for the longest time. So early Greeks, excuse me, 6th, 7th century BC is the first recorded evidence of this. People figured we had a geocentric universe, right? So geo meaning Earth, and centric obviously meaning center. So the Earth is at the center of the universe, and everything rotates around in perfect circles. We obviously now know that that's not the case, but it's a pretty interesting way to look at it. It also makes sense if we're just looking at some of those basic observations, just looking up at the sky. The problem with this is when you start to look a little bit closer, things don't actually move in perfect circles, right? So when you look up there, things don't move in perfect circles. Things are very erratic. Sometimes things are moving faster than they should if it was perfect circles and we were at the center. Sometimes they're moving slower. So the geocentric model doesn't really work out so well. So first person to try and get us out of that is a guy named Ptolemy in about 150 AD. And Ptolemy came up with the idea of epicycles. So the Earth is still at the center, and planets still have a circular orbit. It's just now the planets are moving in circles within that circular orbit. So they're kind of going more like this. Right? Now it's fine. It's like a circle within another circle, right? So here's another diagram of this. And he even placed the Earth away from the center, right? Now this math, he could explain a ton of things within our solar system with this, but it was very, very, very convoluted math. Everything had its own equation. Everything was different. This, it was pretty popular though. Lasted for about 1,300 years. So Earth still at the center, planets and everything still rotating around the Earth, just circles within circles, epicycles. Cool. Copernicus was the first person to ever think, well, probably not the first person to ever think this, but the first person to record and go through and talk about the sun being the center of the universe and the planets are rotating around the sun. Sorry, I should say galaxy at this point, or not even galaxy. What, I'm messing this up. Solar system. Jeez, Murphy. Anyways, Copernicus called this heliocentric, so the sun's at the center, and then the planets are moving around in perfect circles. So again, perfect circles is something about there. Now, you've probably heard about this before. The ideas were too revolutionary. They were not accepted. He was called a heretic, and lots of people lost their lives and stuff over that, which is no good. But it gradually came to light because this model did a much, much, much better job in predicting the positions of the planets than the Ptolemaic system. And it's a much simpler model as well. Right? So this is a big, big, big advance. It doesn't seem like much, but this is a huge advance in our understanding of our world and of our solar system and even of our universe, understanding that we are just a small little speck of dust and everything is not rotating around us. We're not special. So the person who really started to drive things home is Johannes Kepler. Now I realize that that's not the person on the board right now. That's actually Tycho Brahe that's on the board right now. If you ever want an interesting bit of science history, you look up Tycho Brahe. This is at one point, I think he was Danish. At one point, he had 1% of all Danish wealth. Now, 1% doesn't sound like a much, but the entire country's wealth. He had 1% of that, which is pretty wild. Bought himself islands and observatories and things like that. He was a member of the nobility. And probably the weirdest thing is he got in a drunken argument with his third cousin about who was a better mathematician. And they decided to settle that with a duel. And he actually got his nose cut off in that duel and then wore prosthetic noses for the rest of his life, which is, it's wild. Just look this guy up. He's an interesting character. Anyways, Tycho Brahe took just the most ridiculously careful observations about planetary motion using this quadrant system, which he actually invented too, and he did this for 20 years. So can you imagine every night for 20 years, or at least every clear night for 20 years, taking accurate observations and recording them just wild, just a ridiculous amount of information too. So what he actually did with this is he gave it to his student, Johannes Kepler. There he is right there. Kepler's the one that we now know about. Because Kepler, using this data, actually figured out a couple really, really, really important things about how the planets move around the sun. One thing is that, as you can see right here, it's not perfect circles. It's actually ellipses. So law number one from Kepler, every single planet has an elliptical orbit. So not perfectly circular. I don't think I can draw a perfect circle. Better than I thought it would turn out, but not perfectly circular. It's a little bit stretched out, and there are two focal points. Don't worry too much about this, but the thing that is being orbited, so if this is the Earth and this is the sun has to be at one of the two focal points. Now this is obviously stretched out like crazy. Most of the time, they're really, 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 really close to circles, which is why for the longest time people figured they were circles, but they're not all perfect circles, and some of them are less perfect than others, which is why Kepler, well, kind of came up with this, I suppose. The second law that Kepler has is that the planets actually sweep out equal areas in equal times, and we can think about this in a little bit in terms of conservation of energy. So over here on this side, the planet has less gravitational potential energy because it's not as close to the sun. Therefore, it's going to have more kinetic energy, so it's going to move faster along here, so fast, which means it's going to travel a very long distance, but because it's closer, the area that it sweeps out is smaller. Whereas over here, the planet is now further from the sun. Right, so further from the sun means more gravitational potential energy. The height, if you will, is way bigger. And if it's more gravitational potential energy, it's going to have less kinetic energy, so it's going to be moving slower over here. So it travels less distance here, but the area now, because it's further away, is going to be the same amount. Right, so it's further away. So area 1 is equal to area 2. Don't worry too much about these terms, aphelion and perihelion. I mean, if you really want to, you can look into them, but don't worry about them too much. I forgot to take this slide out. That doesn't actually work. So the last one to look at is Kepler's equation. He actually discovered that the ratio of the period squared over the radius cubed is the same for everything orbiting the same object. So for example, here's the sun. Nice. And then I might have Mercury. capital M for Mercury. And then way out a little bit further, I mean, there's probably a couple planets in the way there, but we might have Earth. So Mercury's whizzing around like this, Earth is whizzing around at a different rate, but the ratio of, again, Earth's period versus Earth's radius, a period squared over radius cubed, is going to be exactly the same as Mercury's period squared over Mercury's radius cubed, because they're both orbiting the same thing. So I know in the thing here it says needs to be in meters, needs to be in seconds. That's only if you're using the actual Kepler's constant K. If you're just using the ratio, it honestly doesn't matter as long as the units are the same. Cool, so there is that one. I'm just going to be very, very clear with this one as well. This is kind of bonus material or extra material. So all the math with this one you don't necessarily need to know how to do, but you should have an idea of the big ideas. Sorry. Okay, so we know that, you know, Mercury and Earth have the same constant orbiting around the sun. We could also know that, okay, a satellite and the moon would have the same constant, so the same K value orbiting around the Earth, but the constant for the moon around the Earth is not the same for the constant as the Earth around the sun, right? So only if they're orbiting the same thing. So again, we've got an example here. I'll leave this to you if you want to check it out. It is our enrichment or our bonus material. One thing to kind of note with this is we've got time or period measured in years in both cases. Honestly, it doesn't matter as long as we're not trying to solve for K. And in this particular question, we are not trying to solve for K. We are just looking at the ratio of, let's see, it is, what is it? It's Earth and an asteroid. So E for Earth and A for asteroid. Cool, so that's all we're really looking at with that one. Again, this is bonus material. If you want to try this out, go for it. We're just looking for the mean orbital radius, and we say mean orbital radius because it's the average. Alrighty, so this is, you know, Kepler figured out a lot of important stuff. He did a really good job explaining how the planets are moving around the sun and how the moon is, you know, orbiting around the Earth and stuff like that. But how in science is typically not what we're looking for. We're usually looking for why, right? So Kepler could never figure out why. It's Isaac Newton that figured out why they're orbiting the sun. So the planets are orbiting the sun. And he figured this out using gravity, right? And their idea of their motion is gravity is responsible for their motion. So the story goes, when an apple fell on Isaac Newton's head, he was aware that the apple was pulled down to the earth with gravity. Lots of people say, oh yeah, Isaac Newton, he discovered gravity. But no, he absolutely did not. People were aware of it. People were not flying off of the earth before Isaac Newton made this awesome discovery. What he did was he discovered the connection between the apple and the moon. So if the apple's falling towards the earth and the apple's a mass and the earth is a mass, why wouldn't the moon fall towards the earth as well, just on a much, much, much bigger scale? This is a 9-second video. It is probably the most ridiculous thing you'll see all day. If you want to check it out, that's perfect. Like I say, 9 seconds of your life. It's just one of those things, you know, where you're doing something, you're focusing, and then you stub your toe or something goes wrong. You just get so angry. That's what that one's showing. Check it out if you want to. It's totally fictional and some bleeped out swear words, but whatever, kind of funny. So again, Isaac Newton figured that the apple is being pulled towards the earth via gravity. It is accelerating towards the earth. Awesome. He figured, why wouldn't the moon accelerate towards the earth? But here's the thing with this. The moon would accelerate towards the earth, but it's also got some sideways velocity, right? And now it's starting to look essentially what we were talking about if we just continue this along at the beginning of the unit with circular motion. So the velocity is always perpendicular to the circle, and by circle we're, you know, approximately saying it's a circle. because we now know that it's actually probably slightly elliptical. But so the velocity is tangent to the circle. The acceleration is perpendicular to the circle. That gives us our 90-degree angle. So the moon is constantly falling towards the Earth. It's got some velocity that's going to prevent it from ever actually hitting the Earth. And why is it accelerating towards the Earth? Well, because gravity is pulling it towards the Earth. So this is Isaac Newton's really, really big ideas. And from this, Isaac Newton actually came up with his inverse square law. So I don't know if it is his inverse square law, but it was the inverse square law that talks about gravity in the Earth. So the idea with the inverse square law, here it is. And this is totally not at all related to, gravity yet, but gravity, as with anything, people predict radiate outwards in straight lines. So if here's the Earth right here, the gravity radiates outwards in all directions in straight lines. Now, to talk about this inverse square law, it's helpful to talk about a butter gun. So here's a gun, and here's some melted butter. Very nice. There's our melted butter. And the idea of this is you own a restaurant, a breakfast restaurant at that, right? And you want a butter toast, but you're tired of getting that knife out and spreading it around. So you invent a butter gun. And that butter gun sprays butter onto the toast. Perfect. So it sprays just like, light, just like gravity. It sprays it outwards equally in all directions. So we'll focus on 4 of those right there. And at this particular distance, which we'll call r for a radius, it can butter, and you get a nice thick layer of butter on one piece of toast. So the question is, what happens when we double the radius? So 2 times r. So at a radius of 1, whatever 1 that is, 1 radius, we get 1 layer of butter at whatever thickness. What happens when we get to 2 times the radius? Well, let's check it out. So here's the diagram. I was going to draw this for you, but then I figured that would be a bad idea. So at 2 times the radius, across the top is twice as far. So here was 1, here was 2. But it's a 2-dimensional object. So down the bottom is also 2. What's 2 by 2? Well, that's 4 pieces of toast. If we want to think about how much butter that's getting, so if this had 1 unit of butter on my 1 piece of toast at 1 radius, this would have a quarter as much on each of those pieces of toast. Any ideas what would happen at 3 times the radius? If we expand these lines out, see, and even now I'm doing a bad job of drawing it. Yeah, close enough-ish. That's horrible. Absolutely horrible. But at 3 times the radius, notice we now have 3 across the top by 3 down the bottom. How many pieces of toast do we have to butter? All of a sudden it's 9. That's 9 pieces of toast. That would be 1/9 of the original butter that would have on the first one. So the relationship is, and well, we could talk about butter, right? So the butter has an inversely proportional relationship to the radius squared. Cool? I hope that makes sense for you. So essentially what we're doing, if I double the radius, I'm cutting the butter by a factor of 4, right? Because what we do to one side of the equation, we do to the other side. We can absolutely simplify this. So we square the radius, we also square the 2. So realistically on this side of the equation, we divide it by 4. On this side of the equation, we need to divide by 4 as well. So the inverse square relationship. Take a second and think about this one. What if the radius is multiplied by 3? What happens to the force of gravity? We kind of already saw it. So the radius is multiplied by 3, but then the radius is being squared. So what did we just do to this side of the equation? We essentially divided by 3 squared, or we divided by 9. So the force of gravity would be 1/9 of the original at triple the radius. Cool, so I'm hoping that makes sense for people. Newton actually used this to accurately figure out the centripetal acceleration of the moon, which is pretty rad. So that's our lesson for today. It's a lot of knowledge. We'll be talking about Newton quite a bit more in the last little while, but just as a little recap, see if you can figure out these couple of questions. And then there's another page of questions right away here, just because there is no practice for this. So you can put it on pause. You can think about this. Yeah, go ahead and put it on pause now. Unpause when you're ready. Cool. So you could probably look up most of these, like the Earth-centered model, geocentric, who introduced epicycles, that's Ptolemy. The sun-centered model, that's the heliocentric model. Who introduced it? That's Copernicus. Who went on trial defending it? That's Galileo, which we didn't actually talk about too terribly much. Who first proposed elliptical orbits? Why, that's Kepler. When is the Earth moving fastest? It's when it's closest to the sun. When is it? Oh, it's called the perihelion. Who first explained the planetary? Who first explained planetary motion? Uh-oh, I skipped forward and started giving you answers. Shoot. Anyways, I don't know what to do about it at this point. Anyways, make sure you know what's going on with each of these. We'll leave it there. I screwed up right at the end. Anyways, that is our lesson for today. No practice with this one, but do have kind of an idea of how the story went. And yes, we will be talking about gravity and orbits for the rest of this unit. So bye for now, Physics 20s.